Howdy, and welcome to Mean 315 lecture number 2. Okay, so this is of course our first opportunity to have a recorded lecture. So this is basically the general format of it. I have things written out ahead of time, and you can download these notes off of the e-learning. But it's really important that you listen to the lecture as well, because I give information through the lecture that isn't necessarily written down. So you want to make sure that you listen and watch and generate questions that you can ask in class later on. So to begin, just a couple of announcements to point out. First of all, homework number 1, of course, is due Tuesday at the start of class, Tuesday, January 21st. And the other second announcement, of course, is that our first participation assessment is also on Tuesday. That's part of your homework number 1, is to be able to be prepared for that first participation assessment. So make sure that you have your iClicker ready to go, whether you have an iClicker remote or the iClicker Go app. And then the third thing that I want to mention is that we want to be a little bit, need to clarify a little bit about the textbook. I mentioned that you can get any Chengel and Bowles textbook, but there is one exception to that. They make a SI units only textbook. Sorry about that. Not sure why it's asking me that right now, so we'll just close that. Anyway, there is an SI units only textbook that they offer at a substantially discounted price. But unfortunately, we cover English units this semester, so it's necessary that you have the English units textbook, which includes both English units as well as SI units. Okay, so on Tuesday, the first day of class, we basically left off with a discussion or a question, which was centered on a lump of coal that I had in my hand. And I asked the question, how long can the energy in that lump of coal burn a light bulb, a 60-watt light bulb? And of course, when we look at that lump of coal, I'm holding it in my hand, it may not be obvious to us that that coal has energy or has the kind of energy that we would need to be able to power a light bulb, right? We, of course, can't hold the base of the light bulb to the lump of coal and expect the light bulb to light up. That won't happen. So is it even possible? Does the question even make sense? Can we even ask this question of how long can the energy in a lump of coal burn a 60-watt light bulb? Well, to answer that question, we really need to know how to get started, right? How do we solve this problem? How do we even get started? Well, we can always get started by asking ourselves questions, right? Asking questions is a great way to work through larger questions that we're trying to answer, or larger problems that we're trying to answer. So the first question that we might ask ourselves is, how do we know that the coal has energy? You know, I'm able to hold it in my hand, so it's obviously not excessively hot or radioactive or undergoing some bizarre process that would incinerate my hand or you know, cause my hand to vaporize or something. So how do we know that it has energy? And if it does have energy, how do we use that energy? How do we extract it? How do we release it? How do we get to it? And if we know it has energy, and if we know how to extract it or release it, then how do we know how much energy it has? How do we figure that out? Like what is the quantity of energy that that lump of coal has? Well, to begin, to answer the first question, right, what we need to know ahead of time is that, first of all, everything has energy, right? Everything that we know has energy. The wood that a table is made out of has energy, and the sidewalk that we walk along to get to class has energy, and the air that we breathe has energy. Of course, we know that food has energy, right? That's why we eat it. And this is getting a bit annoying. I hope it doesn't do this all the time. So I'm gonna click that. We know food has energy, right? We know oil has energy. We know fuel has energy. We know the sun has energy, right? But really everything has energy. But what distinguishes energy is that it has certain types. There are different types of energy. And the type of energy that coal has that we use is what we call chemical energy. And chemical energy is that which is associated with holding molecules or compounds together, right? And other types of energy would include things like electrical energy, the kind of energy that we use to power our light bulbs and to power our computers. There's mechanical energy, right? Energy that we use to move things. Kinetic and potential energy are two types of mechanical energy. There's nuclear energy, right? The energy that's associated with fission and fusion and the separation and combination of atoms and the subatomic particles, the components that make up atoms. There's photon energy, the energy that's associated with light. That was actually Albert Einstein's major contribution was a photoelectric effect. And then there's thermal energy, the energy that's associated with, something feeling hot or cold or things having temperature. So all of these different types of energy are all energy, and everything has energy and has different variations or different forms of all of these different types of energy. And we'll talk more about energy as the semester goes along, but so we know that the coal has energy and it has chemical energy. So the next question that we asked ourselves was, how do we extract or how do we release this energy? Well, one way that we can release chemical energy is through combustion. And combustion, of course, is a very common process that we encounter every day. In fact, right now, combustion could be taking place in your apartment or your dorm room to heat your building. But combustion basically involves a chemical reaction of going from reactants to products. So, of course, your reactants in a combustion process are two basic things. You have a fuel and you have an oxidizer. Combustion, by definition, is a rapid oxidation process. So oxidation means that you have to have oxygen as part of the process. You're oxidizing something, and you're oxidizing the fuel, or you're oxidizing the species that make up the fuel. So, in the case of coal, we would treat that as our fuel, and air has oxygen in it, right? 21% of air is oxygen, so that can be our oxidizer. And so you have fuel and your oxidizer, you have coal and air, you ignite, and you have a reaction, and you then go to products of combustion, where in this particular example, our main product of combustion is carbon dioxide. Coal is basically pure carbon that reacts with the oxygen in the air and forms CO2, carbon dioxide. But of course, because combustion occurs so fast, it releases an intense amount of thermal energy. Combustion is a reaction that takes the chemical energy of the fuel and basically transforms it into thermal energy. So that's one way that we can release the chemical energy of the coal, is through a combustion process. Now, that thermal energy is really interesting, and that's actually what we end up using when we use a combustion process. So we need to understand how much of that energy is released during the combustion process. And so using measurements and theoretical analysis, we can actually determine how much energy is released by a fuel, which is, of course, its chemical energy, during a combustion process. Sorry about that. So that measurement, that energy that that is released by fuel during combustion, is called its heating value, the fuel's heating value. And the heating value of a fuel is just a function of the fuel. It's really just a function of the different species and compounds that make up a fuel. So coal is pure carbon, and so if we want to know the heating value of coal, we just need to know the heating value of a carbon reaction. And so it's consistent, right? I mean, coal has a heating value that really varies very little if it has the same carbon makeup. And so we can tabulate these values. We can tabulate the heating values in reference books. And so, of course, this is all now splattered all over the internet. So we can just go online and do a search for heating value of coal, and you'll find a number that's pretty well close to 14,100 BTU per pound mass. Now, if you do a Google search for coal and you find out that it's not this number, well, then look real closely at the units, right? So notice that the units that I'm using here are BTU, or what stands for British Thermal Unit, okay, per pound mass, LBM. So we're going to talk about some of these units because you may not have worked with them before. We of course teach English units in this class, and you'll continue to use English units in a lot of your engineering classes. And so what we need to know is that BTU, it stands for, as I said, British Thermal Unit. And this is basically a unit of energy, which in the metric system, which you're probably more familiar with in terms of your studies, is the joule. So the BTU is to the English system what the joule is to the metric system. It's a unit of energy. It's a way of characterizing energy. Now, this other unit that we stated is pound mass, or LBM. And pound mass is different in concept, but often same in value to the pound force. So, of course, you're familiar with pound force. This is what we usually use to as a unit of weight, right, when we weigh ourselves. And so a pound mass is the mass of a substance, and pound force is a unit of force, right? So you have a unit of mass in pound mass, and you have a unit of force in pound force. So they're different in concept, but very often they're the same in value, and I'll explain that in just a moment. But before we go on to that, let me just describe the physical meaning of this heating value, right? So we said that it's 14,100 BTU per pound mass. Well, what exactly does that mean? Well, what it means is that for every pound mass of coal that I burn, I release 14,100 BTU of energy, right? So you could, in a sense, say that the chemical energy in coal is 14,100 BTU per pound mass. And my combustion process simply transforms that chemical energy into thermal energy, okay? And different fuels, of course, as I mentioned, will have different heating values. Okay, so let's return now to this idea of a pound mass and a pound force. So we say that they're different in concept, but they're often the same in value. So what exactly does that mean? Well, let's use our lump of coal as an example. So let's suppose that we make an estimate of how much our lump of coal weighs. And I just kind of guessed that the coal has a weight. So here this W stands for weight. Okay, and we're gonna use a different meaning of W later on in today's lecture, but right now that W stands for weight. So the weight of the coal, we say, is 2 ounces, right? And of course there's 16 ounces in a pound. So 2 ounces is the equivalent of 1/8 of a pound. Now, that's a unit of weight, which weight, of course, is a force, not a mass. And so this pound, this 1/8 pound, is the force unit, or pound force, okay? But we don't need to know the coal's weight. We need to know its mass. So we have to somehow figure out the mass of the coal based on this 1/8 pound force. Well, that's straightforward, right? We learned that in physics, Newton's second law, which is represented by the equation force equals mass times acceleration. So in this case, the force is the weight, and the mass, of course, is the mass, and the acceleration is the acceleration due to gravity, which in the English system, this acceleration constant is equal to 32.174 feet per second squared. So I can manipulate this equation, my quote-unquote Newton's second law equation, and say that the mass of the coal is equal to the weight of the coal divided by gravity. Well, I have these two parameters. The weight is 1/8 pound force, and the gravity is 32.174 feet per second squared. But if I look at that, I have pound force divided by feet per second squared. Now, if this were the metric system, this would be a kilogram, and the denominator would be meters per second squared. And we know, or we learned, that a kilogram per meter, a kilogram second squared per meter, or a kilogram per meter per second squared, if you will, is the definition, or the precise definition of a Newton, right? So kilogram per meter per second squared is a kilogram, but we don't have quite the same corollary in the English system, right? In other words, 1 pound force per foot per second squared does not directly equal some other parameter. So this actually leaves us with goofy units, right? We get these units of pound force second squared per feet. So there is, in fact, though, a conversion, right? So we need this to be in units of pound mass. So we have to go from these units of pound force second squared per feet to units of pound mass. And that conversion factor is given here in this box. 1 pound force is exactly equal to 32.174 pound mass feet per second squared. Now, it's very convenient that this conversion factor is numerically the same as the acceleration due to gravity in the English system. Because what this does, when we impose this conversion factor, is it in fact cancels the pound force, cancels the feet, cancels the second squared, and cancels the 32.174. So what did I do here in this line? Well, this first part here, where we have mass of coal is equal to an 1/8 pound force divided by 32.174 feet per second squared, is exactly the same as what we have up here, okay? But then I multiply it by our conversion factor. So 1 pound force is equal to 32.174 pound mass feet per second squared. And because the 32.174 is the same in the conversion factor as the acceleration due to gravity, they cancel, and all the other units cancel aside from pound mass, and we see that the mass of the coal is exactly equal to 1/8 pound mass. Now it's a mass, it's no longer a force, but numerically it's the same as the weight of the coal. And the whole reason why is because of the conversion factor that's defined. The conversion factor is defined to essentially allow the mass of a substance in pound mass be the same as the weight of the substance in pound force when you're in standard acceleration due to gravity. And that's what this statement here is saying. When you're in standard acceleration due to gravity, that is when g is equal to 32.174 feet per second squared, 1 pound force is the same as 1 pound mass in value. Different concepts. This is a force unit, this is a mass unit, but numerically they're the same values. Okay, so now we know how much energy the coal has per unit mass. That's this heating value that we looked up on the internet, this 14,100 BTU per pound mass. We also know how much mass we have, based on our estimate that the coal weighs 1/8 pound force, which is the same as 1/8 pound mass. We know how much mass of the coal we have. So to find the energy that the coal has, that our coal has, the 1/8 pound chunk of or lump of coal, we simply take the mass of the coal and multiply it by its heating value. And so we say that the energy of the coal is equal to 1/8 pound mass times the heating value, which is 14,100 BTU per pound mass. And that comes out to 1762.5 BTU. So our little lump of coal has 1,762.5 BTU of energy. Now, that number probably means absolutely nothing to you. I mean, if you had heard of a BTU before today's lecture, you probably didn't have a real strong physical sense of it. And so really, we could say that the energy of the coal was 16,456 thingamabobs, and it would have the same feel or physical relevance to us that saying 1762.5 BTUs has for us. So we're going to see what that amount of energy will do for us later on. That's part of answering this question, is to get a sense as to how much this energy, or how long this energy can power a 60-watt light bulb. Okay, so now we know how much energy our coal has, and we know how to release that energy. That's what our combustion process does for us. So the next question is what is combustion, right? I mean, we talked about how it's a reaction where we go, it's an oxidizing reaction where we go from reactants to products. But what really is it? Say from a thermodynamic point of view, what is combustion? Well, I briefly mentioned it, but we've gone ahead and written it down here, that combustion is basically a process that converts chemical energy to thermal energy. We're transforming energy. The coal starts as having chemical energy. We release that energy during the combustion process, and that released energy is in the form of thermal energy, right? In case you've ever used a grill before, you know that that puppy gets hot when you're burning coal, and that therefore is the result of the combustion process in the conversion of chemical to thermal energy. Well, let's draw what this might look like, right? So this is our lump of coal. This little thing here is our lump of coal, and it's burning. That's what these lines here represent, right? So this is probably one of the nicest looking drawings that I'll make all semester long. That's not my talent in life, drawing, but hopefully you get the idea. This is a burning lump of coal. And of course, that lump of coal has chemical energy. And in that burning process, it's releasing thermal energy, okay? And it's releasing the thermal energy to the surroundings of this lump of coal, right? So this big old circle that I have drawn here is represents the surroundings, right? The coal is in some kind of surrounding, and it's releasing that thermal energy to the surroundings. So first of all, the first thing that we need to note is that this flow of thermal energy, so see how I have that arrow there, and that's describing a flow of thermal energy? We call the flow of thermal energy heat transfer. And we use the letter Q to represent heat transfer, okay? So let's now, using this information, let's now take this situation where we have this burning lump of coal burning in its surroundings and converting chemical energy into thermal energy. Let's now represent it in a way that we typically represent things when doing thermodynamic analysis, right? So we first of all don't necessarily call it our lump of coal. Instead, we call it our system, okay? So the system is the region in space that we're interested in. It's what we're performing analysis on. It's what we're studying. The system is what we study. So you remember drawing those free body diagrams in Physics 218 and Mean 221 or Civ 221, whichever you had. It was just free body diagram after free body diagram, right? Well, the system in thermodynamics is the equivalent of the free body diagram in particle dynamics and particle statics, right? Things like Mean 221. So we'll need to continue to use this terminology and use this concept. And all you need to know is that the system is what we're studying. It's what we're interested in. Now, as we talked about in the diagram above, this system is interacting with surroundings. Most often, the system is in some way interacting with the surroundings, right? And in the case of our burning coal, the interaction is the release of thermal energy into the surroundings. So what are the surroundings? Well, the definition of the surroundings is the space outside the system that is interacting with the system, okay? So we have our system, our lump of coal, and it's burning, and it's releasing thermal energy, Q, into the surroundings. So, of course, Q is our heat transfer from the system to the surroundings. And even though I draw the arrow in this direction, it's important to note that mathematically, we would say that the heat transfer Q is actually negative for the system. It's losing energy, right? It's giving up its energy. And so that's a negative flow of energy for the system, but it's a positive flow of energy for the surroundings. Okay? Okay, so now we know how to release the energy. That's our combustion process. But how does that help us, right? So I know that I have got this 1,762.5 BTU of energy, and I know that I can, douse my coal with lighter fluid and, starting fluid and toss a match on it, and eventually my coal will start burning and smoldering in the grill. But how can I use that in that combustion process to power a light bulb, right? I'm trying to power this light bulb, and I want to know how long I can power it for. How does any of this help me? So before we said that we can't take the light bulb and just touch it to the coal and expect the light bulb to light up. But does having the combustion process help us in any way? Can I burn this coal and release thermal energy and put my light bulb close to the thermal energy and expect it to just start shining, it to light up? That's what these three lines represent, by the way. That's meant to indicate that the light bulb is glowing, right? That the light bulb's lit up. So can I do this? Can I just light a fire and stick a bulb up to it and have it start shining? Well, no, right? That's a silly idea. We're not able to do that. A light bulb's an electrical device, right? It works by resisting the electricity through the filament, and that causes the filament to get white hot shining, and that's what gives us the light. But we need electrical energy to the light bulb. We don't need thermal energy. The combustion process is giving us thermal energy, but we need electrical energy for the light bulb. So what do I do? How do I go from this Q to electrical work? Am I now done? We talked about some cool things. We learned about BTUs, and we learned about pound mass, and we talked a little bit about combustion and burning things, and that's always really fun and cool to do. But but so what? Maybe I'm done. Maybe I can't power this light bulb with the coal. Well, in fact, we can. And the way that we can use this thermal energy to produce electricity is by using something which is called a heat engine. Okay? So what is a heat engine? Well, a heat engine is a cyclic device that converts thermal energy into work energy. That's the definition of a heat engine. And electrical energy is a form of work energy. Okay, so we're in fact able to use a heat engine to go from thermal energy, which is what the coal is giving us, to electrical energy, which is work energy, which is what the light bulb needs to be powered. So let's take a look now and see what an example of a heat engine is. And the most common example of a heat engine is in fact the steam power plant. So I know that pretty much all of you have heard of a steam power plant, right? And there are steam power plants all over the world. And we have a couple here in the Bryan College Station area. We actually have one right on campus. It's that building that's across the sort of kitty corner to Blocker, and across the street from the North Side Garage, and across the street from Thompson on the other side, along Ross Street there. And so a power plant, a steam power plant, is a heat engine. And what happens inside a steam power plant is you have a cycle, okay? And we'll define a cycle in just a little bit, but basically a cycle is a collection of processes where a substance that's flowing through each of these processes undergoes various physical changes. And you make use of those physical changes to perform the function that you want that cycle to do. So in this case, the cycle is meant to take thermal energy, QH, and produce work energy or electrical work. And so here now you'll notice I have some W's drawn on this diagram. Those W's now represent work transfer. And from this point forward, we will probably always use W to represent work transfer. So what happens inside a power plant is, first of all, if it's a coal power plant or natural gas power plant or some other type of combustion power plant, you have a smokestack on it, right? So that's what this little thin line, these parallel lines here, sort of parallel lines, are meant to represent. That's your chimney from a power plant, your smokestack. And you have coal, and you're mixing that coal with air and you're burning it, and that goes to products of combustion. And those products of combustion are what are going out the smokestack, out into the atmosphere, okay? And of course, the other byproduct of the combustion process that we want to use is the thermal energy, okay? Now that thermal energy is at a very high temperature. It's burning coal, right? It's very hot. And so we use the letter H to indicate that this thermal energy is coming from a high temperature process, that is the combustion process. Well, we then add that thermal energy to one of the processes inside our power plant, which happens to be the boiler process. Now, a boiler is, as what it's named, it boils something. And in the case of a steam power plant, steam, of course, is water, right? Steam is vaporized water. So a boiler is boiling liquid water on the inlet side and making it steam or vaporized water on the outlet side. Now, of course, that steam is really hot, very high temperature. It's at a really high pressure. And so we can use that high temperature, high pressure steam and cause it to spin a turbine, right? And now a turbine, of course, is like a fan, if you will. It's a series of blades that are connected to a shaft that is centrally mounted, right, or concentrically mounted in the turbine. And as the steam flows past the blades inside the turbine, it causes the shaft to spin. So we then have this shaft that comes out of the turbine, and we then connect that shaft to a generator. That's what this GEN stands for. And of course, a generator takes shaft work, this W shaft, and converts it into electrical work. And so we actually are generating the electricity here. And then we take that electricity and we pass it through power lines. That's what these are. Those are power lines. And then we run them into our houses and we use them to power our various appliances and light bulbs and computers and everything else that takes electricity. But that's not all for the cycle, right? So after the steam passes through the turbine, well, now it's at a lower pressure and a lower temperature. But it's not at as low of a temperature that it needs to be in order to work properly in this cycle. So after we pass through the turbine, we have to pass the water through a condenser. And the condenser removes all of the temperature or thermal energy from the water that isn't helpful to us, that we can't otherwise use. And that thermal energy that's being transferred out of the condenser is then cooled in a lake or a nearby river, or sometimes there's a cooling tower. We have cooling towers on campus that our power plant uses. And then, of course, there's a pump in this whole process that gives us our high pressures and causes the water to circulate nicely throughout the cycle. And of course, that pump requires work. So we have work that we have to pass into that pump to make this all happen. Okay, but the gist of what's going on here is that there's a work transfer from the turbine to the generator, and we call that shaft work. That's what this little symbol here says. It says W shaft. There's a T missing there. Sorry about that. And then there's the work transfer from the generator, which of course is the electrical work, right? The generator is taking the shaft work and producing electrical work. But all of this started with the thermal energy that was being added by the coal. So this is how we take this heat engine device, this is how we take thermal energy, this QH, and convert some of that thermal energy into electrical work. Okay, that's how a power plant works. Okay, so we input QH, that's our thermal energy from burning the coal, and we output electrical work, right? That's what we want. And so we basically can say that we get electrical work, but we pay for the coal that gives us the QH, the thermal energy. So naturally, right, we want to maximize the electrical work, that's what we get, and we want to minimize QH, that's what we actually have to pay for, right? We have dollars coming out of our pocket for that, so we want to minimize that. But that ratio is called thermal efficiency. And thermal efficiency is a real important concept that we'll continue to talk about the rest of the semester. We use the Greek letter eta, right? It looks a little bit like an N. We use the Greek letter eta, ETA, to describe or to represent the efficiency, the thermal efficiency. So we mathematically represent the thermal efficiency as what we get divided by what we pay for. Or sometimes people will call it the output divided by the input, and that's fine too. So for our power plant, our output is the electrical work, and our input is QH. So, what is a typical efficiency for a power plant? Well, you probably won't believe me when I tell you this, but it's on the order of about 40%. What does that mean? It means that for every unit of energy that our fuel provides, that our coal provides, we're only converting 0.4 units into something that's actually useful for us, the electrical work. Useful in the sense of work energy. So that might seem atrociously low to you. I mean, you might see that number and think, oh my gosh, I can't believe it's so low. I can't believe it's not like 90%. Like, what's all this stuff we hear about ultra high efficiencies and 90% efficiencies? And I mean, seriously, it's, steam power plants are getting 40% efficiency. Well, the truth is that this efficiency can never be 100%. We can never completely convert thermal energy into work energy, okay? And beyond that, aside from the fact that it cannot equal 100%, but there's actually a theoretical limit that will cause the efficiency of a heat engine to always be less than 100%. And we're going to talk about that later on this semester. It's a really important concept that we will certainly revisit. But if we assume that the simple power plant that we're using for our lump of coal to power our light bulb has an efficiency of 40%, well, then what that means is that the electrical work that we can get from our burning lump of coal is about 705 BTU, right? Our efficiency is 0.4, and our thermal energy input is 1762.5 BTU. This is the amount of energy that our burning coal has. So I just take this equation here and I manipulate it to solve directly for the electrical work, or electrical work is equal to eta times QH. And so that gives us 705 British thermal units. Okay, so we're making good progress now, okay? We know that by burning the lump of coal, we can ultimately deliver 705 BTU of electrical energy, right? That's what this number tells us. But we now run into another question, and that is, how do I use that information, right? How do I use the fact that my burning lump of coal can give us 705 BTU of electrical work? How do I use that information to determine the time that it will light a light bulb, right? How do I use this to determine how long I can power a light bulb, a 60-watt light bulb? Well, so that's one thing that we need to remember, right, is that we know that it's a 60-watt light bulb. Well, what does that mean? Well, of course, to say that it's a 60-watt light bulb means that it uses 60 watts of power to light, right? So when I plug a 60-watt light bulb into a light socket and I flip the switch, that light bulb is using 60 watts of power. Well, what is power? Well, power, as you probably learned in physics, is energy per unit time. So if I say that power, and I use W dot, where dot is meant to represent a time derivative function, and we say that power is equal to W dot, well, that is just equal to the work energy, or the energy, per unit time, T. Okay? So I can now manipulate this expression and say that T is equal to W divided by W dot. And now I just have to recognize one important detail, and that is that the watt is a metric unit of power, right? A watt is exactly, so here now inside this bracket is meant to represent watt, right? So that's, when I use the brackets like that, it's indicating the unit of watt, okay? So the unit of watt is exactly equal to 1 joule per second. But our work energy, if we go back up here, is in English units of British thermal units. So we have to somehow convert. We can't improperly mix units. We have to keep everything in the same system of units. So I choose to convert the 60 watts into the English units. And so we can look up the conversion factor, and we learn that 1 kilowatt is equal to 3,412.14 BTU per hour. That's provided to us in a conversion factor table. So now I can convert my power of the light bulb, which is 60 watts, which is, of course, 0.06 kilowatts, into BTU per hour, which is just 204.73. So now, if I go up to this equation here, where T is equal to W divided by W dot, W is W electric. That's the amount of energy that the amount of electrical energy that the burning lump of coal provides for us in a simple steam power plant. And I divide that by the power that the bulb uses, which is 60 watts, or 204.73 BTU per hour in British units. And so now we just plug that into our calculator, and we find that the time that our bulb is lit would be 3.4 hours. So that little lump of coal that I held in my hand in class on the first day of class has enough energy in it to power a 60-watt light bulb for almost 3.5 hours. It's pretty neat stuff. Now, of course, all of you are very familiar with the new mandate that essentially has outlawed filament, or the incandescent, as they say, light bulbs, right? And so a 60-watt light bulb, essentially is an incandescent bulb, and they're now being replaced by CFLs and the other new light bulbs, and they use a lot less power to deliver the same intensity of light. So we can ask ourselves, what would happen if we redid this entire example, instead using 10-watt CFL bulb instead of our 60-watt incandescent bulb? Well, it actually results in a big difference. That little lump of coal can now power a 10-watt CFL for more than 20 hours. So it makes a huge difference to move to these smaller powered bulbs, the CFLs, compared to the incandescent bulbs. Okay, so we talked a lot and about a lot of different things in that example, and so it's kind of instructive to sort of summarize exactly all of the concepts that we discussed here. So, some of these concepts are things such as using English units versus metric units, and the concept of power versus energy, and the concepts of pound force and pound mass. We learned that there are different types of energy, and the specific examples that we looked at were chemical, thermal, and electrical energy. We also learned that we can transform energy. We transformed the chemical energy of the coal into thermal energy, which we then transformed into electrical energy. So we were able to change the types of energy through various processes. We learned about efficiency. We learned how to define efficiency and what that means for us. We learned about systems and surroundings. Remember when we had the diagram of the coal as a system and it was transferring thermal energy into the surroundings? And we also learned about processes and cycles. Okay. Now I'm going to take a little bit of time and define more precisely for you some important terms such as process and cycles, but a couple of others as well. So first of all, a process, right? When we were talking about the simple steam power plant, I said that it operates on a cycle, and a cycle is composed of processes, right? And I said that the boiler was a process, and the turbine is a process, and the condenser is a process, and the pump is a process. But what does that mean, right? What's the formal definition of a process? Well, a process is an action that causes a system to go from one state to a different state. Okay, so let's go back up to our diagram and take a look at our power plant. So we said that the boiler is a process, right? So what is the boiler doing? Well, remember, we said that the boiler takes liquid water and makes it into vaporized water. So I start off at one state where water is a liquid, and I move, because of the process, to a different state where water is now vapor. And of course, it's able to do that because the boiler adds thermal energy from the combustion process. But the boiler itself is a process, just like the turbine is a process, the condenser is a process, and the pump is a process. Okay, so I used a new word there in that definition, and that new word is state. So what is a state? Well, a state is an existence of a system in equilibrium that can be characterized by properties. So when we were before the boiler, we had liquid water. So I can characterize that liquid water by saying that it has a certain temperature. I can measure that temperature. It has a certain pressure. I can measure that pressure. And I know its phase, right? I know that it's a liquid. So water exists at a state at that condition. Likewise, after the boiler, water is vaporized. It's at a much higher temperature and it's at a much different pressure. So it's characterized by a different set of properties, which consequently means that this water is at a different state. So we also use this word equilibrium in that definition. And I'm not going to get into, so equilibrium is, of course, equilibrium. So the way we define equilibrium is, like you might think of equilibrium, for example, as being a balance of forces, which is, to a certain extent, absolutely true. The definition that I like to use for equilibrium is that it's a condition where no gradients exist. And we're gonna spend more time talking about equilibrium later on, so I'm not gonna hound it right now, but just know that this is how we define it for thermo, is that it's a condition where no gradients exist. Now, the other term that I used earlier is this idea of a cycle, right? And I even defined cycle in words, just talking earlier, and said that a cycle is a collection of processes where the properties of the system after the final process are the same as the properties before the first process. Okay, so what does that mean? Well, let's go back up to our power plant. And let's suppose that the first process in the cycle, it doesn't really matter which one it is, but I'm just going to arbitrarily say that the first process in the cycle is our pump process. So that's the first process, and just before the pump is before the first process, right? And I can use properties to characterize that state. It'll have a certain temperature, a certain pressure, a certain phase. And then I go through the pump, and now I'm at a different temperature, perhaps a different pressure. I'm probably still the same phase as a liquid. But then I go through the second process, and of course now I'm at a different pressure and a different temperature and a different phase. And then I go through the third process, where now I'm at again a different temperature and a different pressure and perhaps a different phase. And then finally I go through the last process, the fourth process, where now after the fourth process, after the final process, if this collection of processes is operating as a cycle, then the properties of the substance after the condenser will be exactly the same as the properties of the substance before the pump when the cycle began at the first process, right? In other words, the properties at this point, right here where my hand is, are always the same. And if it's truly operating on a cycle, it doesn't matter where I said my first process is. It could have been here before the boiler, and the same is true, right? These properties never change as the substance moves around the cycle, right? The properties of the substance change as it goes through the different processes, but if I just fix myself at one spot in the cycle, then those properties don't ever change as the system operates on its cycle, okay? So that's the definition of a cycle. That's an important definition, and we'll come back to that again. Of course, we're going to come back to all of this as the semester moves along. Okay, so now it's time to start getting into some of the nitty-gritty about how to do this various thermodynamic analysis. And to do that, to start to get into the rigors of the analysis, we need to provide some stronger definitions to this idea of a system, right? Remember the equivalent of a free body diagram, and how the system can interact with the surroundings, okay? Well, to begin, we have to realize that there are three major types of systems. The first is what is called an isolated system. Now, the isolated system is perhaps the most important from a theoretical point of view, but it's the least important from a practical point of view, okay? The reason why is that an isolated system is just as it's called. It's by itself. It's alone, right? It doesn't interact with anything. It's just by itself. So an isolated system does not exchange mass, energy, nor entropy with the surroundings, okay? It's just all by itself, period. Doesn't interact with the surroundings. Now, as I go through the definition of these systems, you'll notice that I'm talking about three major things: mass, energy, and entropy, okay? So we're going to talk about these three things more in the next few weeks. Mass, of course, you're pretty familiar and comfortable with, but we're going to talk more about energy and entropy later on in just a couple of lectures, okay? But for now, just know that a system, an isolated system, does not exchange any of these three items with the surroundings. So the second system is now a very important system from a practical point of view, and that is the closed system. So a closed system can exchange energy and entropy with the surroundings, but it cannot exchange mass with the surroundings, okay? It's closed, it's sealed, if you will. So no mass can get in and no mass can get out, okay? But it can exchange energy and entropy with the surroundings. And if you're wondering, well, how does it exchange energy if it's not exchanging mass? Or how does it exchange entropy if it's not exchanging mass? Don't worry about that detail just yet. We're going to come back to these ideas more in the next few weeks. The third type of system is what is called an open system. In the case of an open system, it can exchange mass, energy, and entropy with the surroundings. Okay, it can do all three. So we go from a condition of none of the three to a condition of possibly all three: mass, energy, and entropy. Okay, so in the definition of these three systems, the most general, of course, is the open system, right? So I'm going to draw this, or I'm going to show this diagram. And this diagram is going to be something that we're going to look at many, many more times this semester, okay? This is basically a thermodynamic representation of an open control system, an open thermodynamic system, okay? Now, how do we know that it's open? Well, we know that it's open because there's mass flow. That's what this arrow and these terms here represent. So m dot, right, we know that m represents mass, and the dot, of course, represents the time derivative, or the rate of mass. So this m dot is the mass flow into the control system. Likewise, there could be mass transfer out of the system, and that's what this m dot out represents, is the mass flow rate out of the system. So we have mass coming from the surroundings going into the system in the case of m dot in, and we have mass coming from the system and flowing into the surroundings in the case of m dot out. Now, in addition to the mass flowing into the system or the mass flowing out of the system, that mass, of course, has both energy and entropy. So we use the letter E to indicate the energy of the mass, and we use the letter S, lowercase s, to represent the entropy of the mass. And so in parentheses, I just say E in, comma, S in, to indicate that we could have, or that we have both energy and entropy that is coming in with the mass or being taken out with the mass. Okay, we can also, of course, transfer energy in the form of heat transfer. So this is how, for example, a closed system could exchange energy and entropy with the system through heat transfer. So this Q dot here represents the energy transfer by heat transfer. And then, of course, we can also transfer work transfer. So this W dot represents the energy transfer by work transfer. And then the final thing to note in this diagram is that with all these interactions, right, mass flow interaction with the surroundings, thermal energy interaction with the surroundings, work energy interactions with the surroundings, entropy interactions with the surroundings, with all of these interactions, we can cause the system itself to change with time. We can cause the mass of the system to change, the energy of the system, or the entropy of the system, okay? And that's what this dm by dt, dE by dt, and ds by dt represent. So dm by dt is how the mass of the system changes with time. dE by dt is how the energy of the system changes with time. And ds by dt is how the entropy of the system changes with time. So if we think about our coal, our lump of coal as an example, as our system, as we were burning that lump of coal, we were changing the energy of the system. dE by dt would have been negative as we were burning the coal, because the coal starts off as having chemical energy, we burn it, and we release that chemical energy to the surroundings in the form of thermal energy. But the coal itself, now, because we released that chemical energy, has less energy in it than before we started the combustion process. So dE by dt in that case would be negative. We decreased the energy of the coal. We decreased the energy of the system. Okay, so now there are three laws that we use to analyze this system from a thermodynamic point of view. Okay, so we will repeatedly consider three laws this semester. And these three laws are thus. The first is conservation of mass. The second is conservation of energy, which is also known as the first law of thermodynamics. And then the second is what is called the second law of thermodynamics. So, of course, conservation of mass, I'm sure you're familiar with it. mass cannot be created nor destroyed. Conservation of energy, of course, is that energy cannot be created nor destroyed. The second law you may not have heard before, and this one doesn't have a nice little simple statement that we can attach to it like conservation of mass and conservation of energy do. But all the same, I try to have as simple of a statement that we can use at this point in the class to describe for you what second law does or what second law says. And basically, the second law of thermodynamics states that processes are limited or constrained in how they proceed. So what does that mean? Well, let's think about our lump of coal example. When we had our lump of coal, it was this chemical energy that we had bound up in a lump of coal. How it got that way, we don't really know, right? There were millions of years of natural processes that took place to get it into that condition, but that's the condition that we have it in right now. And when I burn that lump of coal, the process is going to go in a direction. It's going to go in one direction. It's going to burn the coal, it's going to oxidize it, it's going to make products of combustion, and it's going to release thermal energy in the process. So at the end of the process, I have basically ash from the coal, I have thermal energy that's been released, and I have carbon dioxide, my product of combustion. What do you think the likelihood is of the three of those things spontaneously reforming themselves into a lump of coal? Just imagine taking a lump of coal and putting it in a sealed box and somehow igniting it, a sealed box that had oxygen in it, and enough oxygen to burn the coal completely. And I ignite that coal and it burns and it releases all the thermal energy inside the box, but the box is really well insulated so that none of the thermal energy can leave. And so I have now inside my box ash, carbon dioxide, and thermal energy. Will those three things recombine to make a lump of coal? Absolutely not, right? It's almost funny to think of it, right? That's what the second law says. The second law simply says that processes are going to go in a limited number of directions. And there are certain things that will not happen. And the second law basically says that recombination of carbon dioxide, thermal energy, and ash into a lump of coal is not going to happen. It's physically impossible. So we'll get a chance to come back and talk about this, all three of these laws, in much more detail as the semester goes along. But what's important is that these three laws give us three governing equations. And so these three governing equations are the following. And by the way, this is what I'm looking for. This diagram here, with all these various variables and these different definitions, are what I'm looking for in your problem number 3 in homework number 1. So these three laws basically give us these equations. The conservation of mass equation says that the change in mass of the system, dm by dt, is equal to the mass that flows in minus the mass that flows out. It has to be conserved, so it's a balancing equation. It's an accounting equation. Likewise, the conservation of energy tells us that the change in energy of the system, dE by dt, is equal to the heat transfer minus the work transfer. And we'll talk about why that minus sign is there later on, but for right now, just know that it's there. Plus the energy that flows into the system with mass flow rate, minus the energy that flows out of the system with mass flow rate. And then finally, the third governing equation comes from the second law of thermodynamics, which basically says that the change in entropy of the system with time is equal to the entropy that transfers with heat transfer, that's this integral q dot divided by t term, plus entropy that flows in with mass flow rate, minus entropy that flows out with mass flow rate, plus a fourth term, which is unique to just the second law of thermodynamics, and that is entropy generation. And so entropy generation is a really neat idea. It's a really important idea, and we will talk more about entropy generation as the semester moves along. And it's a lot of fun to talk about it. Okay, so those are your three governing equations from our three major laws that we will study continuously this whole semester. And this concludes lecture number 2. So if you have any questions, please feel free to post them to the discussion board or stop by my office or ask them in class on Tuesday. Otherwise, I hope you have a good weekend. Stay safe, and we will see you on Tuesday.